Good evening, everyone. Welcome to the second session of the day. I am Sri Krishna Sudhamsu, a postdoctoral research from the Department of Applied Mechanics, IIT Madras. I have known the speaker of this session, Professor C. Lakshmana Rao, for several years as my supervisor and teacher during the course of my PhD at IIT Madras. Today, I am fortunate to have the pleasure of introducing him. Professor Lakshmana Rao has done his BTech and MS degrees from the Department of Civil Engineering, IIT Madras, in the years 1982 and 1986, respectively. He has then graduated from Massachusetts Institute of Technology with a Doctor of Science in Mechanics of Materials. Since then, he has been working in the Department of Applied Mechanics, IIT Madras. He has worked on several industrial projects and has published extensively in various international and national journals of repute. His research lab, known as Miles Lab, works on several engineering problems related to damage mechanics, impact mechanics, fracture mechanics, finite element analysis, traditional medicinal systems, and many more. It is not an exaggeration to say that he is one of the few researchers who willingly works in any area of solid mechanics as long as the problem has an engineering end value. Professor Lakshmana Rao is also a man with vision towards development and nation building. He is actively involved with various academic and non-academic societies within and outside IIT Madras. As some of you all may know, he is one of the founding members of the Indian Society for Applied Mechanics. It is my honor to introduce him, and I welcome him today to deliver his talk on broad overview of issues in modeling of materials. Thank you, sir. Professor Lakshmana Rao, you may please deliver your talk. Thank you.
Thank you, Dr. Sudhanshu, for a nice introduction. Let me just directly go on to what we are supposed to do in this introductory lecture. I would like to thank my co-author Naushad, who helped me in putting this material together so that we get an idea as a good kickstart on what are the issues that are involved in what we are trying to do in this entire workshop. So I thought I'll put together my own thoughts or the thoughts that we have been having on the general issues that people have been working with over the past few years on this concept called modeling. So let me just go over to go. So what we will go through, we'll have a good review of the mechanical testing methods that are normally done on metals and perhaps on many other materials, and look into some failure micrographs, briefly go into the historical review of modeling of inelasticity in metals. Then we'll look into micro defects and mechanisms that are responsible for this inelastic deformations. We'll look into some history of the damage and also look into some fatigue response of metals. Then give you a brief touch of unified mechanics theory, about which Professor Chamal will be developing much more elaborately, and give you a small summary within this 1 hour that we have here. So there's a lot that has been going on in the literature or by the researchers in the broad concept called modeling of materials, and modeling of metals to start with, and then people are also concerned with modeling of other materials. So metals slowly flow into non-metals, and therefore people are interested in non-metals which are in the form of ceramics, polymers, and so on. But when you go back into the literature, especially when you go back to the history of modeling, you find that initial work has always been done on metals, and the concepts from metals have been borrowed and used in various other materials, be it concrete, be it soils, be it composites, and so on. So many of them try to pick up on some of the models that have been developed for metals, not knowing fully well that what is developed for metals cannot be copied exactly as it is, and perhaps has to be developed in a different manner for other materials. So therefore, it is good to know about metals, especially to know how people have been copying these concepts in other materials, and perhaps to avoid such blind copying whenever we are working with other materials. And that's why I thought this broad overview will help. So let us go over to the next topic, which is on mechanical testing of materials. This mechanical testing testing methods are very important, because proof of the pudding is finally in the eating, and everything has to be calibrated and validated with the reality. And the reality is with reference to what you see in what you see in tests. And what are the tests that people do? People can try to pull things in tension or compression, or perhaps do some shear tests and so on, and get some graphs of various types under different conditions, under different loading rates, under cyclic loads and so on, and get some nice graphs, and perhaps try to capture those graphs using models. So the entire business of modeling has to be validated only when you only with experiments, and doing these experiments is not always easy. And therefore, it is good to know what experiments we can do, what experiments we cannot do, and how we can generate good experimental results even with limited test facilities that we may have in our own respective colleges. And this is where I think a lot of collaboration is required, especially when you want to be close to reality. So let us go through what goes on in mechanical testing, and especially we did this classification to look into the ways in which you can classify these materials in terms of, this testing, in terms of the strain rates that are associated with these testing methods. So you can work with speeds which are of the order of 0.001 to about 0.1 meters per second, and then which are translated to speeds of the order of 5 to 100. The specimen sizes are of the order of 5 to 100, and also with time scales that are of the order of 1 second to about 1 hour. And so this is what we call as quasi-static, and this is where we develop most of our machines, because our applications are mostly in this range. But you can have slowly deforming materials which are in the creep zone, which will have materials that are having time scales of the order of 10 to the power minus 4 seconds or 10 to the power minus 8 seconds, which is very low. At the other end of the extreme, you can have materials being tested with a very high strain rates, which is of the order of 10 to the power 4 per second and so on. So depending upon the range in which you are testing the materials, you require different equipment to test these things. So most of the times we focus our attention only on the quasi-static range of loading, and within that itself there is quite a range of testing that can be done. In the recent time, there has been a lot of interest in rate dependent testing or high strain rate dependent testing, and recently we also started doing some work of this high strain rate dependent response of materials. So we'll go into the type of tests that can be done to capture each one of them separately. So now when you look at the stress strain curve, which is what we ask all our undergraduates to plot in their strength of materials labs, you will expect them to generate some curves of this type, where you try to plot the engineering stress with something called as a, which you measure as strain. You can convert the strain into nominal strain and convert the engineering stress into true stress and get these responses. This is typically done when you buy any machine which is capable of doing it, and depending upon how you want to capture this graph, whether you can have either a load controlled machine or a displacement control machine, or a servo hydraulic machine which can control both of these at some at your will. So if you want a displacement control machine, then that's the only way you can capture all these interesting peaks that are coming into this material. Now, what is it that is of interest to us is always a question. Do we really want to capture the entire load history? Yes, perhaps. And sometimes are we interested in the modulus? Are we interested in the strength, ultimate strain? And is that enough? So these are the questions that we need to keep asking ourselves each time that we do these tests. Most of the people in materials lab think that it is enough if we report maximum stress, ultimate stress, or yield stress, and perhaps the elongation for break. They really don't care whether you are able to plot these graphs with all their angularities of various types. They may be interested as an engineer. In fact, you may not be interested in knowing anything that is beyond yield. So you focus your attention only on the ultimate strength or yield strength, and after that you may decide that the material has almost failed. So even today, many materials labs report only these values whenever you ask for test data on any new material. Very few of them will plot the entire stress strain curve from the beginning till the end. And as scientists, we may be interested in finding out what the stress strain curve is at various stages. And why are we interested in finding the stress strain curve at various stages? It's because that we are also interested in using these materials response curves in what we call as numerical modeling of the response of a structure. And that is why you require a model which can capture this entire response. And so this is the challenge that we face, and there's always a debate between pure material science people and those who are coming from mechanics standpoint of view. The borders are slowly changing. Many people from materials background are also looking into modeling and trying to see the value of these full stress strain curves. So associated with each part of this curve, there is a different thing that is happening within the curve, and that is important to note here also. So, for example, what you will have is a different mechanism that is happening at different stages, and these mechanisms are something that you may want to capture. There's something called damage, depending upon what you define as damage, that is taking place right from the beginning. And whether the material is damaged or not will be known only when you do some unloading tests. And very few people have the patience of doing a full loading and unloading test whenever they deal with materials. So some insights in the material cannot be obtained unless we go deeper into the cycles of loading in the material. So these are the things that we have to keep in mind as we go deeper into modeling aspects of the material. So let us go into other type of tests that are possible and that are necessary to be done whenever you are dealing with materials. If you think that your material is isotropic, you don't need to really do any other tests other than the one that I have shown earlier. I mean, because isotropic material will mean that you have same properties in all directions, not only elastic properties, but also failure properties. And therefore, you really don't need to do tests in different directions. This is very important to note, because all our models that we are going to develop during this entire course will be multi-dimensional in nature. They will all talk of tensors, they will all talk of multi-axial state of loading. But just because you have multi-axial state of loading, do you require multi-axial state of stress, a state of state of testing is not well understood by people, and therefore this needs to be very carefully understood. So in the recent times, people have developed multi-axial state of multi-axial testing apparatus also, where you also you test material both in tension and also perhaps in torsion. When you perhaps Professor Chellapandi, when he gives his lecture 2 days later, he will talk about some special phenomenon that will take place, especially when you are twisting your material in torsion in a cyclic fashion while keeping your tension intact. So again, we are now talking about plastic deformation. So unless if you are entering into a plastic deformation, then there's an anisotropy that is definitely coming into play, and therefore it is required for you to do tests in different directions. If you are still within the elastic limit and you think that material is perfectly elastic and doesn't undergo any dissipation, you really don't need to do cyclic tests, and you really don't need to even bother about testing things in multi-axial state of loading. So multi-axial tests have been developed in the recent past. They are there of two different types. You can have a tension or compression combined with torsion, which deals with multi-axial state of loading, or you can have a biaxial testing apparatus, which is of the following type, where you have testing in two axes which are in plane. Okay, we have in IIT Madras, we have some apparatus which can do both these things, biaxial state of stress in on thin polymers, as well as tension torsion type of tests on metals. And I would say that they are underutilized. And anybody who is interested in doing these tests are welcome to collaborate with us, and or at least see how we can use these things more effectively. So, but for most of the applications, you don't require these. Testing is an important thing that you need to know. You require this whenever you know that a material is anisotropic, because when you have an anisotropic material, both in elastic deformation as well as in plastic deformation, then definitely there is a need to do tests in different directions, or tests in combination of two different directions. And that is an important thing to note, not only for metals, but also for other materials. And some special labs are working on these things, and it's not always required to do these tests. And there's enough challenge even without this multi-axial testing that needs to be done. So moving forward, there is also a need to do the tests at high strain rates. And in the recent past, especially over the past 10 to 15 years, there has been a great rush in trying to do these tests at high strain rates. About maybe 10 years ago, building these things was very prohibitively costly, and therefore people who are working on high strain rates simply don't do the test, or borrow the material that is available in a model and a package like Adina, like LS Dyna or Abacus. Plug in materials, plug in some values, and generate some results. In the recent past, doing these tests is now becoming affordable. We have recently, after a lot of tapas, I would say, we have established a high strain rate facility here in IIT Madras, where you do see, just to give a broad idea of what it involves to do these tests, you can see in your screen something like a gas gun which will uh, you know, which will push a bar at a very high velocity, which will hit an incident bar. Incident bar will later hit a specimen, and that specimen, then there'll be some pulse that is transmitted through the transmitted bar. And by capturing signals both from the incident bar as well as the transmitted bar, it should be possible for you to get these full stress strain curves at different strain rates. So some of those things are shown in the graph next you see here. And these are important primarily because your yield stress can keep changing depending upon the rate at which you're loading the specimen, as you can see in this figure. So when you go from a quasi-static test to a very high strain rate test, which is of the order of 17,500 per or 1750 per second, you find that the yield stress drastically changes, even though it falls off very equally drastically after some time. And therefore, capturing and the modulus more or less remains the same, even though the yield stress changes a lot. And this is an important thing to, only thing that you can do to capture this is by doing an experiment. And this has been in the literature for quite some time, and people have been trying to capture this entire thing through various models. So moving forward, you also have tests that need to be done in cyclic loading. And again, in the olden times, people were simply monitoring the number of cycles to failure and develop something called as a Wöhler curve, which served some purpose to find out how much your material can withstand, how many cycles it can withstand, and so on. And when you have a combination of these cycles, people were just combining what they defined as a damage under various loadings, and then try to predict the life of a structure. It's not all the predictions that are made are all astrological predictions, I would say. Many of them are not really validated. If at all they are validated, they are validated over a limited range, but definitely they are believed to be true even for the projections that they are expected to do. So if you do a simple test on these for cyclists, you will find that the stress strain curves can change a lot depending upon the number of cycles that you subject them to. And this is what you see in these curves here. And this is an important thing to capture the full hysteresis curve under the as you keep increasing the number of loads. And it is mainly to capture this change in these graphs as you change the number of cycles that people have developed various models, both in plasticity and mainly in plasticity. And therefore, what has attracted, what has really captured people's attention is not only to define the yield, but there is something called as a hardening that takes place beyond the yield, and there is a reverse plasticity that is taking place when you unload the material. And this cycle can keep changing as you proceed with the number of cycles. And therefore, it is really important to capture these changes as you go along. So a lot is going on in this. A lot more needs to be done, and this is the broad direction that in which the people have been going. So proceeding further, if you look at the stress strain curves at different rates, some of you are working on high strain rates, you find that there is a wide range of behavior and that needs to be captured. If you take some material like copper, the initial modulus seems to be okay, but afterwards there is a lot of change with the non-linear portion of the curve, which keeps changing with strain rates. If you take a material like concrete, not only the post peak behavior changes, but the initial modulus itself keeps changing, and you have different strengths that are achieved depending upon the type of loading rate that you have here. Okay, So, and similarly, when you're talking about a polyurea, a metal polymer like polyurea, the strains involved are quite large. They are of the order of 1.2%, etc. And you find a wide range of post quote unquote yield behavior in the polymer. So the terms like yield, etc., are actually relevant for metals, but they have been borrowed and used very loosely even for other materials, and therefore it's good to know what they really mean, what they originally meant, and what they should not be used for. So, for example, when you see a curve like this in concrete, you should just call it as a nonlinear curve, nonlinear sustained curve, and not use terms like yield, because there's nothing called a phenomenon called yield that is taking place in concrete. But many models that are used in concrete have used uh, uh, plasticity models, and they have tried to develop these things. So therefore, this is an area which requires a lot of improvement, not only for concrete, but also concrete-like materials like ceramics or rocks and so on. And that's why we need to learn to do things differently. So moving forward in this story, now that we have looked into testing of these materials. In the recent times, you can merely test a material, it is not accepted. People want to know what happens at the failure surface of the material. So therefore, people have been reporting failure micrographs and different failure micrographs. I mean, there's something that's it's an art that needs to be learned by all of us in at different stages, depending upon the uh, the microscope with which you see, you will see different features of the same material. So here you see two different zoom positions of a micrograph. One is at the 100 microns micron length, and the other is at a 10 micron length, and you will really see different textures that are showing up. And the signatures that are seen at the 10 micron length scale are clearly different from the signatures that you see at 100 micron length scale, and therefore there's a length scale dependence in the observed features in a material. Not only and consistent with what you want to capture at which length scale, your modeling strategy can also be different. And that's where there's a lot of research that is going on, which many of which are going to be developed in this course. So whenever a metallurgist sees this graph, he is able to identify them easily as a ductile fracture, and treat it as a ductile material, which is distinctly different from what you see in the next graph, which is that of a cleavage fracture. A brittle material undergoes a cleavage fracture, and many of you here are interested in fracture mechanics. And it is not as structured as what you saw in the previous graph, and therefore there are brittle the signatures that you see in a brittle fracture, that means that the failure, are definitely distinctly different from what you have in a ductile material. So that is what you see in the left graph, and what you see on the right graph, right, this one is basically a signature that you see for a fatigue failure. So there is something called as a beach marks that are seen, because there is always a cyclic loading, therefore it will keep on going up to certain thing, come back, reverse plasticity, and again it will start building up and so on. So there will be something called as a beach mark that is seen in the micrograph, which will which is a signature of fatigue failure. Fatigue failure means a number of cyclic loading due to failure due to cyclic loading, progressive failure due to cyclic loading, and finally there will be a complete cleavage of the material. Okay, so these are the things that will uh, prompt you to look at distinct cracks in a material. So there are a lot that has gone on in analyzing cracks in materials, and with the hope that with analyzing some single crack, you will be able to get a better insight into the material. failure overall in an overall sense. Part of it is true, part of it is not true, because material is a conglomerate of many similar features, and just by capturing what happens in a single crack, it is unlikely that you will be able to predict the total failure of a material. So these are the things that we have to keep in mind when we are dealing with modeling of materials. Okay. So going forward, depending upon what scale and what length scale and what stage that you're observing materials, there are certain things that you see which are obvious, as you see in the top right hand corner micrograph. Okay. But what is leading to that particular failure thing is a postulate. And that postulate is also equally important. And people develop these postulates starting from stage 1 to stage 2 to stage 3, as you see in your graph, where you start with some randomly located dislocations that slowly get oriented in a particular way. And then they all form some elongated subgrade fracture uh, subgrades formations, and then they all coalesce together and then finally form a signature of some type. So if you want to look deeper into this, okay, that's all about that thing. And then so these are the micrographs that you see of various things that may take place within the material as you keep going, as you keep loading. And the attempt now today in modeling is to be honest and say that the models that you're capturing are true to the micrographs that are captured at the end of the failure of the material. Unfortunately, you cannot examine the material, examine the insides of the material at various stages. You may know what is at the beginning of your loading, and you may know what is there in the after it has completely failed. In between, what it is going through is not something that you can always observe. You can have a postulate. Perhaps people have their own intuition of what is happening in the material, but many of these things cannot be visually looked into, and that's an important thing to note whenever we are talking of modeling. And that is also the reason why there are different types of approaches, the different postulates, and why things are going on in different directions when you talk of modeling of metals. So let us quickly go through these issues. The term called modeling, now we are coming into modeling. We have looked into experiments, now we will now look into modeling. There is something called as a constitute continuum model, which is used in continuum mechanics. Basically, it is, when you look into take a course in continuum mechanics, they look at constitutive model as something which bridges the gap between the stresses and strains. So you require something that connects the two together, and that's why these models are important, is what they will say. And then there are different things that are being called as models. There is something called, people call as analytical models. Analytical models are some things that you can do by simple calculations. Some things you can predict by simple mathematics of various types. And therefore, and many times the analytical, so-called analytical models have limitations in their range of applicability. And that is where you require a numerical model which can capture some of the features from analytical models and develops on it. And so, for example, stress concentration around hole, etc., can be developed analytically because you are assuming that the material is linear elastic. Okay, so it's more in terms of what happens in perfect solids, perfect geometries like holes, like holes or spheres in infinite geometry, in infinite domains, can be captured through analytical expressions. And mathematicians love to develop these analytical expressions. They like elasticity because there's only a few parameters that you can deal with. They like infinite domains because it's easy to derive solutions in that. and these equations that they develop, their solutions that they develop are fascinating, sometimes mind-boggling, and so on. And so it's up to us to use them in the right way and take the best information from it, and then to throw the rest. So these are the issues that are there in the literature on analytical modeling. The analytical modeling is not preferred when you are dealing with plastic deformations. And in the recent, this discrete modeling is something that is being done by looking deeper into each atoms and so on. And that is what you try to do when you cannot capture the overall behavior and you want to go deeper into the material. And if you go much more deeper into the material, you end up with the molecular dynamics type of modeling, where you look at it from the standpoint of molecules, atoms, and so on. So that is where you end up with statistical modeling. So depending upon the type of question that you ask, you can choose to adopt any one of these methods and then get some answers out of it. Okay, so with this broad background, let us go deeper into the history of plasticity in general. So,
Professor, so
what
what is
is
actually involved in
yeah,
multi-skill modeling?
yeah. No, so we have not come deeper into that. We'll just go. We'll first look at macro scale modeling. We'll come to my multi-scale modeling later.
Okay, okay.
Is there any comment that you want to make?
No, actually, I want to understand that, just curiosity.
You want to understand what is multi-scale modeling? Okay, fine. We'll take that up. Basically, in my own understanding, multi-scale modeling is to looking at a material at different scales. And just as I've shown in the micrograph, where we have seen the same material, when you look at it from different scales, my 100 microns and 10 microns, you see different features. So to capture those features, you'll have to develop models at each scale. And therefore, and to switch from one scale to another is what is broadly going on under the what we call as multi-scale modeling. We'll get deeper into it as we go along. Right now, we are taking a very engineer standpoint of view. First, let us understand what is happening at a single scale, a macro scale, then go deeper into the micro scale. Okay. So let us go back to what we have learned in strength of materials in terms of the origins. So when you look at yield, I mean, or inelasticity, that means the deviation from elastic behavior, which is in the form of yield. It goes back to Saint Venance or Tresca, who has simply postulated that a material will fail when its strength reaches a particular value, and it is isotropic, and strength reaching a particular value is isotropic, whether it is in tension or compression, it is the same. And when you have a combination of tension and compression, some linear interpolation between the two is what is postulated. So this is intuitively very appealing, and it's postulated way back in somewhere in I think way back in 1864. So we are more talking about at least 1.5 decades, 1.5 centuries earlier, where people have postulated these models. And I mean, that's a stress-based failure criteria. And of course, later, so you can come up with a displacement or a strain-based failure criteria, and a combination of a stress and strain, which results in a energy-based failure criteria. So all this failure, when you say failure in these cases, they all mean yield. Okay, so they all tested things on metals, and whatever is called as yield in metals is called as failure. But it's a different matter that this failure criteria, the so-called Tresca failure criteria, is still being used in brittle materials like concrete even today. Okay, so whereas much more is learnt about metals, And what is known today as a failure criteria for metals, which is popularly used in all things, is something called as a von Mises criteria, which is based on distortional strain energy. Okay, so when you try to plot it in the principal stress direction, it will, in the stress plane, it will turn out to be an ellipse, which we'll see later will turn out to be yeah. So if you want to capture what Tresca tried to do, which was, I think, was also developed by Saint Venance and others, is that you require a spring which captures the deformation, and an elastic deformation. That means it can unload until you reach a critical point, and after that it starts slipping, just as a frictional block slips past a surface. And therefore, his earliest concept of plasticity is a spring slider, friction slider type of model that he has used, and which seems to be working well for such an observation. And that's where things have started way back about in 1864 and so on. So now moving forward from that, and we are going really then you have von Mises, who developed the concept of principal planes or principal directions or principal stresses, and started looking at things in a principal octahedral stress plane. And so octahedral plane is something that is equiaxial with reference to the three principal axes. And when you look at the evolution of the material, see, please note that all of these are discussed in a multi-axis state of stress, even though the tests are done in uniaxial tests. And therefore, it is important to note that all models are multi-axial in nature, but most of the time they are validated with uniaxial tests. And this is an important lesson that all of us should learn when we come to modeling. So when you test it with equiaxial tension in all the three directions, then it is postulated that you will reach a yield in which is in the form of a circle when looked in the octahedral plane, and that circle will keep expanding as you keep loading the material in the form of yielding. Okay, so that yield is captured in the form of an expanding circle that was postulated in by von Mises. I mean, this figure is taken from 2016 paper, but the concept is of von Mises way back, 1928. So we have jumped from 1864 to 1928. That's about 2 decades. I mean, more than 50, 60 years of development in plasticity. Then there was a concept of bringing in the influence of the mean stress in the evolution of the stress in the evolution of the yield surface. So even though there was some developments by Prandtl in 1924, what you see is what is attributed to Drucker in 1949 and Prager in way back in 1945 is a realization that your mean hydrostatic stress will play a role in determining the yield surface. And therefore, if you have a higher mean hydrostatic stress, then you will have to do much more work to reach the yield. And this is a very important concept which is again being debated in today in terms of multi-axial role of hydrostatic stress and constraint effects in yield of material. So what has been talked about as a debate here today is being visualized in the and postulated in the form of a model way back in 1940s and so on. So these are the developments. I will quickly pass through these things so that we have more discussions. So the way these things have been developed have been evolved. I mean, these yield surfaces evolve over when you keep loading are the ways the plasticity theory has developed in the various directions. And you may note that all of them are slightly mathematical in nature. They are trying to postulate different forms of these equations of the yield surfaces and so on. If, for example, you see the yield surface is something to do with the deviatoric stress in three different planes. and capturing all those things in the form of some graphs, and similar things have been happening. So all of them don't really have an insight into the way, into why different things are happening, or what is happening inside the material which is responsible for this varied behavior in a particular metal. And therefore, translating it from one metal to another metal is not all that easy. So you'll have to develop these things independently for each material. And therefore, these are being called as phenomenological models and looked down upon as phenomenological models by many of the people who are working, doing research in the recent past. Okay, so this is what we need to know in terms of yield phenomenon in metal. So there are further developments by Nagdi, Green and Nagdi and so on. We'll just skip all this and go over to the next topic, which is on micro defects and mechanisms in elasticity. So, I mean, a lot has been talked about on these defects, on the role of voids. I mean, everything starts. So when you look at a metallurgy, one of the first things that you are taught in metallurgy is the cause for plasticity is the presence of dislocations, and dislocations are nothing but misplacement of atoms in a perfect solids. Okay, so and if they are totally misplaced with reference to each other, then you have something called as a vacancy, and the movement of these vacancies is responsible for many phenomenon uh, like creep and so on. So people talk of these phenomena in solid states, solid state physics, and that is what is being talked about even in metallurgy uh, literature. And today it is possible for you to look at these dislocations and get their signatures by looking at the transmission electron microscope. And it's possible to look at the material and recognize that these are the dislocation signatures that are there, and movement of these dislocations are the basis for various models that are developed from a micromechanical standpoint of view. So when you agglomerate all these dislocations, you have other signatures like twin boundaries, and they have boundaries of various types. There are twin boundaries, the twinning of materials, which is some sort of a shearing, and then there is something that is happening at the grain boundaries. Many of which is postulated and sort of intuitively arrived at, and based on what happens at the grain boundaries, you can postulate as to what is happening into various phenomena that is going on in a metal. So now these are intuitively postulated by material scientists. Now people in mechanics are trying to capture those effects and incorporate them into models in of various metals. So now there is various things that are there. I mean, we'll not go deeper into these things at this stage. There's the dislocations. There are like 9 dislocations. The dislocations keep moving and they collapse with each other, form a small disk, and they keep further moving further is what is postulated. I mean, the animation that you see is only a postulated mechanism. It is not something that is observed. What you observe is in the what a single signature, as what you see in the figure that is on the left side, and everything else is a nice animation to help you to understand it in a better fashion. Okay, so let us move forward. I want to really have some discussions because I seem to have put too much material in here. But anyway, let us go through this. There's an interesting thing about damage, and there's something that people should know about damage mechanics as we go along. And this is an interesting thing when even as we were looking into various concepts of damage in the literature, we find that the term damage has been used ubiquitously by different people meaning different things. And unless you really define precisely what you mean by damage, it's difficult to talk in the same language with different people. And that's a basis for development of various things. Now, for example, when you go back to some traditional when I'm talking of traditional classification of materials, even by philosophers, in the Indian philosophy, they have something called a concept of dravya and guna. Dravya is the material and guna itself properties. So the any one of them can get disintegrated. The dravya itself can get disintegrated, material can get disintegrated, it may lose what it is supposed to be initially, and all its properties can change. So unless you define which property you are changing, in which way, what is deteriorating, it's difficult to talk about these things in a single way. And therefore, we looked into the dictionary definition of damage, which says that it is a physical harm that imparts that impairs the value, usefulness, or normal functioning of something. So the value means here they mean about its true worth for how much you have paid to get it, as well as its usefulness. And so therefore, when you talk of all these things, value, usefulness, normal functioning, etc., you're talking of properties, you're talking of gunas of a material. Or at a different level, they talk of when they talked about damage earlier, they talked about development of cavities and so on, and so on, which will result in deterioration. Basically, they talked also of dravya in the terms of how see, a solid is something that will put everything together, it retains its shape, etc., they say, at a broad level. So therefore, presence of a cavity or presence of something will slowly, even though at a broad level it maintains its shape, something is disturbing its ability to maintain its shape, and that is called as a damage. So you have something inside entering in the form of a cavity or something else, which will sort of try to loosen it out and disintegrate its material itself. So that's another definition of damage. And you have concepts of people from a chemical standpoint of view, chemical engineering, they also talk about damage, which is more in the form of the bonding between the various constituents of a material. So that's again a property that is being changing. And when you come to thermodynamic definition of damage, they are talking about something called as a loss of energy, loss of elastic energy, or loss of some energy that is resulting because of various things that you do to it. And the dissipation is defined as a dissipation of energy, or energy that is in different forms, and bring in the concept of entropy, which keeps increasing with time. And so these are the different concepts of damage that you see in the literature at different times. And basically what you see as damage mechanics has been developed by somebody called Kashanov in way back in 1958, and he dealt with as though it was a disintegration of dravya, which is the material. And he developed as though there is a void, and void keeps growing, and the number of voids keep coalescing with each other, and therefore it causes disintegration. When material science people, or when designers talk of damage, they think that it is something that happens at the fag end of its life, which is in the form of cracks, micro cracks. All of micro cracks come together and form macro cracks, and therefore that causes a deterioration. Anything that is closer to yield, they will not call it as damage. It's a definition that they have by themselves. So whereas lack of properties, lack of elastic response, it takes place even at the type of yield of a material. So that is not defined as damage by in the classical literature. So whereas from a different standpoint of view, in terms of lack of properties or lack of guna, it loses its ability to respond in a particular way, and that can still be defined as a damage even at the stage of yield. So whenever we to use the term damage, it is difficult. It's important to define it in the proper way and take it forward from that definition. And that is what will be discussed at different levels as we go along in this course. And it's a very interesting debate that we will enter into as we go along. So we'll skip many of these things. These are different definitions that have come and so on. Now, this is an interesting. We look. I mean, these are type of different models that have been developed. The Johnson Cook has defined his own damage. So people start use damage as an equivalence to some parameters. Wherever you have some parameters that are not fitting up the thing, then you call it as a parameter. And when you don't find anything else, you call it as a damage parameter. So that's what Johnson Cook did when he looked at stress strain data of different materials and their failure curves and so on, and he fitted them with curves and called each one as a damage parameter. So don't get confused, they are just parameters. They are not, the damage is just a name. It may not mean anything, and this has to be very carefully understood. So we put together this nice table which talks about places where you have the change in properties, whereas also a change in, for example, if you took a later change in density, it is more in the form of change in the matter or dravya. Whereas when you look at elastic modulus or ultrasonic wave velocities, etc., all these things have been used in the definition of damage, and this is what you find in the literature. And it's good to just see which term is used as damage in which context, and just keep track of it. And when you're dealing with writing papers in that particular domain, it's good to go along with their definition and just go along with it, even though you may not agree with their definitions from a different standpoint of view. Okay, we will. This fatigue is an important thing that we will be dealing with. I myself will be talking about it during the workshop. Again, this fatigue and Euler's curves have been used. They define damage as the number of cycles to failure divided by total number of cycles, and then when you have a combination of this, you simply combine small n by capital N and say that everything together should be less than 1. So we don't know from where they have picked up all this, but it may make sense in a particular, from one standpoint of view, and that is accepted as absolute standard, and people produce PhD thesis in defining this term called damage. As long as the community accepts it, that's fine, but you ask deeper questions about it, it may mean nothing. So this is something that I have seen when I've looked at all these things on damage. So we'll come to close this lecture soon. We have something called unified mechanics theory. I'm not going to talk too much about it now because Professor Chamal will be talking about it. Basically, it is trying to combine the Newtonian approach to integrity of the material, where we define some properties, and the concept of entropy that has been put together by Boltzmann. And combining these two, Professor Chamal says that there's no material which is perfectly intact, and everything undergoes a degradation right from the beginning, and it's important to put them all together when you are trying to assess the integrity of a material. So more about all this you will hear later, and perhaps I will just stop here.